Now we're going to talk about percentages. This is the kind of the big idea of percentages. Actually, let's just start that over. This really should be times 100%. Percent is the part that you're interested in divided by the whole thing times 100%. So here's my example. James is my oldest son. He's now a junior in college. But his kindergarten class had 15 boys and 5 girls. Doesn't that sound fun? What percentage of the class were boys? 75. These numbers are easy. We understand boys and girls and numbers like 5 and 15. Well, let's look at how we did that. Okay, the whole class is the boys and the girls. It's 15 boys plus 5 girls, which is 20 children. The part that we're interested in is the number of boys. So the part is 15. So the percent boys is 15 over 20 times 100%, which gives us 75% boys. And you cannot tell me that percentages do not have application in real life, because they do. You go to the store and it's 25% off. It's helpful to understand what percentages mean. Percent can also be thought of as parts per 100 parts. Per cent. How many cents in a dollar? 100. How many years in a century? 100. Per cent. Per 100. So this 75% is the same as 75 boys per 100 children. Were there 100 children in his kindergarten class? No. But this is the same relationship. If 75% of this particular population is boys, then the percentage you'd be able to figure out, if there's 100 children, 75 would be boys. If there were 200 children, 150 would be boys. We use percentages in chemistry referring to elements and compounds. So same idea here. The mass percent of an element is like figuring out how many boys are in the class, how many grams of this one element is in the mass of the entire compound. So let's look at iron 3 oxide and calculate the percentage of iron. So the percent iron, and this is by mass, the mass percent, will equal the grams of iron, that's the part, divided by the grams of the whole thing, times 100%. What happens to the units there? They cancel out, don't they? When you calculate a percent, the unit is always percent. I don't think we've done much with that yet, but in other classes I'm seeing these lab reports and they're telling me that the percent error is, 5 grams per milliliter. It's not a percentage. They did the math right, but then they just stick a different unit on there because they think they should. I don't know.
If you multiply it by 100%, you get the same number. If you do it by 100, then you get the percentage. It changes the decimal place. But if you do it by 100% and put it in the calculator, it keeps it the same.
Your calculator's weird. Calculators understand percentages a little differently, and Excel understands, if you tell it you want it to express numbers as percentages, it'll multiply by 100 for you. You don't enter the percent sign on your calculator when you do
You're just
this.
doing it by 100.
Yes.
Okay, I got you.
Yeah, that's a completely different issue. That's your calculator being programmed to do some fancy stuff. My calculator doesn't have a percent button.
It's on the second shift button. Mine's by the 2, the red button.
Oh, it
2.
does, look at
I
that.
was looking and looking.
Yeah. Don't use the percent button on your calculator. It'll screw you up every single time. Okay, so this is the equation we need, the part over the whole, the mass of iron divided by the mass of the entire compound. What's the mass of the compound? What's the mass of the iron? They didn't give us any masses. What do we do? Well, we make something up. Isn't that good? We just make something up. What would be convenient? Because, see, the percentage doesn't depend on the sample size. If you had 500 children, if you have 20 children, if the percentages, it's the same. So what's convenient is to say, let's use 1 mole. So we're just going to choose 1 mole for this calculation. Because then we can use the molar mass, and that'll tell us the mass in grams of the compound, and we can use the molar mass of the iron, and it all works out really nicely. So 1 mole of Fe2O3 weighs how many grams? Well, it's 2 times the mass of iron and 3 times the mass of oxygen. We just learned how to do that. In fact, we just did that, didn't we? No, that was the other class. I just calculated this one. That number looks really familiar. So 1 mole of it weighs that much. What's the mass of iron in there? That would be this part, right? In 1 mole of that compound, there's 2 moles of iron. 2 times 55.85. This is 111.7 grams of iron. So calculate the molar mass of the compound. In 1 mole of this, we have 2 moles of iron, which was 2 times 55.85. We have 3 moles of oxygen, 3 times 16. We get the whole thing weighing 159.7 grams. What mass of that is from the iron? Well, it's this part. We just calculated it. We wrote it all out. This would be the mass of the oxygen, and they're going to add up to this number. So here we have the mass of the iron. There we have the mass of the iron oxide, and we put them in the equation. So this equals 111.7 grams divided by 159.7 grams times 100 equals 69.94. So in iron 3 oxide, 69.94% of the mass is from the iron. The rest of it is oxygen. Any questions?
What material for this one? For say variation?
Why 4 sig figs? The molar masses that I used had 4 sig figs. And so then this rounds to 4 sig figs. If I used more accurate molar masses that had more digits, I could include more digits in my percentage. It's a good question.
And then the iron in the formula that you wrote,
Mhm.
you don't have to put the FE2 on top? Because that would be the part, or,
That's not the pointer part. This is the point. So the question is, do I have to put a 2 up here somewhere?
the part.
Because it's Fe2. Well, we're calculating the mass of iron, and so when we look at this formula, we said, well, what's the mass of iron? Well, there's 2 moles of iron, and so we do the 2 here. Okay? Any other questions? I think there's another example coming. Morphine. Morphine is derived from opium plants and has the potential for use and abuse. Blah, blah, blah. Do we need to know that? No, we don't. Its formula is C17H19NO3. What percent by mass is the carbon in this compound? Well, percent carbon would be the mass of carbon divided by the mass of the entire compound. So first let's figure out the mass of 1 mole. So again, we're going to choose 1 mole as our amount because it's easy. So 1 mole of morphine has 17 carbons, 17 moles of carbon, and 19 moles of hydrogen, and 1 mole of nitrogen, and 3 moles of oxygen. That's a decimal point. Yeah. You can do this all just straight through on your calculator. 17 times 12.01 plus 19 times 1.008 plus 14.01 plus 3 times 16 . 285.332 grams of C17H19NO3. That's equal to 1 mole. What mass of carbon is in 1 mole of morphine?
204.17 grams.
That's the mass of carbon, right? So we've got 204.17 grams of carbon in 1 mole of morphine. It's a long formula. There's some big numbers in it. With the colors, it really looks like kindergarten stuff, doesn't it?
Looks like Christmas.
It's Christmas, yeah. I'm not going to talk about Christmas. So I found the mass of carbon in 1 mole of morphine, and I found the mass of 1 mole of morphine. So now we use the equation, and we take the mass of carbon, so the mass percent of carbon equals the mass of carbon, 204.17 grams, divided by the mass of the whole substance, times 100, 24.17 divided by 285.332 times 100. 71.56% is carbon. Which of those is the best answer? D.
So when doing percentage, do we always have to round up? Or
No, you always, the question is, when we do percentages, do we always have to round up? Well, no, you just follow the rounding rules.
Well, I mean, round in general.
This is multiple choice, and so then they've decided to use 3 significant figures, where I used molar masses with 4. Is it essentially the same number? Yes, it is.
But you always choose the best answer.
For multiple choice, you choose the best answer. 71.6 and 71.56, the only difference is that they've used 3 sig figs and I've used 4. And so, I would not say, well, that's not exactly what I got. I'm not going to choose that one. And that's why I'm not a big fan of none of the above, because here there is no none of the above, right? So you can't choose that one. If there was, don't choose that one. Okay, if you came up with a number like, 1.5%, then none of the above might be a good thing.
So this is applicable in pharmaceutical. If they have a 250 milligram tablet of prescription drug, and then they have a 500 milligram, you're going to see what the ratio of your medications in that molecular structure for more milligrams.
Yes, you can do things like that.
So they have caffeine, you have a percentage of caffeine related to the whatever it's called.
There's a lot of calculations of this sort that come up in medicine, whether in pharmacy, for doctors prescribing medications, or for nurses interpreting what the doctor said and giving a dose appropriate to the weight of the patient.